Good afternoon. It's quite a treat to be able to talk about my work in front of a captive audience because I don't know about you, but having not been in academia for a while, you go to a dinner party and you say to an electrochemist working in wastewater, and you watch how quickly people go for drinks and for the toilet, and your conversation definitely doesn't last more than a minute. So having 20 minutes is quite a treat. Wrong way. But today, actually, rather than wearing my scientific electrochemist hat, I'm wearing more the commercial hat. And lithium's role in radar was the commercialization of the technology. And because we're an SME, we're driven by commercialization. And despite our objective being treatment of water and wastewater, it makes sense to be aware of what are the emerging markets, what are the emerging challenges, and the technologies that will come to deal with those. And so, although our main focus is the development of electrochemical technologies to treat wastewater, knowing and sensing what's on waters and in the environment as a means to then deploying our technologies is something we have a lot of interest on. And because we've taken our technologies from the fundamental science of being in the lab to having industrial scale systems, we've actually learned a lot about the process of going from lab to market. And it's from that perspective that we've come into radar with a view of contributing with our commercial experience and certainly with our interest in the commercialization side. And radar came at quite a right timing, because when we first got involved in the project and we started talking to industries, and looking around for media coverage on endocrine disruptors. There was not much out there. And over the last 3 years, we've gone from talking to companies who said, actually, we're aware of it, but no one's forcing us, we're not going to do it, and to public who was not aware at all, to now seeing programs on BBC and sort of broad stream media coverage. So radar has come at quite a timely moment in this subject. And so we know now from all the science that's been done on endocrine disruptors that this is a significant challenge. Now it's here to stay. Endocrine disruptors are ubiquitous in the materials we use, plastic being one of them, and so finding them in the environment and removing them out of the environment is a challenge that we'll have to deal with. But the industry, as I said before, was not really aware of this, or I mean, if you're wearing a commercial hat, you understand it. I mean, they were aware, but if your job is removing things out of an effluent, and you need to make money out of it, and someone is telling you, well, you're going to have to remove more stuff, and by the way, they're in really low concentration, so it's going to be really hard, then it's really not in your interest. And so industry will do it if, A, the public is aware and drives it, so if the consumer is aware, and the legislation to impose those measurements encourage business to do so. And having said that, I mean, the applications are, or the market potential is huge. I mean, and we saw this morning the presentations. Actually, I found it really interesting, and I never thought about it that way, not being an hydrologist, the mapping of the basins throughout Europe, and how really that extends over political borders. And clearly, that presents a huge challenge in monitoring those areas and developing consistent, reliable, and timely data. And so there's a huge commercial potential there for deployment of sensors and sensors that can operate autonomously in the environment. And so the commercial applications are actually quite wide. No, I mean, in terms of environment, prevention and monitoring of specific sites of value. From the industrial point of view, I mean, anything to do with process monitoring that controls the quality of your inputs and your outputs. From a health perspective, I can certainly see it that we'll get to a stage where we're hoping to get to sensors where you can screen people and get outputs in real time for specific compounds that cause health issues. And certainly in the scientific community, in R&D, I mean, there'll be a continuous need for hardware that allows us to detect various analytes. So the commercial potential for it is quite big. And a bit like Stefan already mentioned this morning, when you're going to produce a piece of equipment that fulfills the requirements, you'll have to go through an exercise of specifying what those requirements are. And what we often find, having become more applied scientists rather than pure scientists, is that the challenges of making science or a bit of science know-how into a product are actually not the hardcore science, are not the fundamental principles, are the everyday challenges of the environment in which that bit of hardware is going to be deployed. I was speaking to Florian, which I think is going to present tomorrow on the radar instrument. And he was giving a really good example of the kind of challenges that we face. After all the thinking and the efforts put into understanding the principles, actually one of the big challenges that they've come to realize is possibly the material involved in the tubing on the sample extraction from the environment might be actually working as an interferent, and therefore you might be losing lots of sensitivity. And it's the menial day-to-day things and these kind of engineering challenges that really are the route to making a bit of scientific know-how into a piece of hardware with commercial value. But if you're going to have something with commercial value, certainly these are sort of broad, this is a broad list of parameters that you want to look at. The one that particularly comes to mind to me is the ability to have autonomous instruments. And if we're ever going to cover all the basins in Europe, for instance, and monitor water quality, I think there's little chance of having an exercise in generating that comprehensive database that we talked or that we heard about this morning, unless we have something that can stay in the environment and collect the data and send it wirelessly to a centralized database. I mean, there's the effort in monitoring on a day-to-day basis. All the sampling sites required is huge and it's time-consuming. So those parameters, you know, the robustness of having a piece of kit that can live in the environment, can be subjected to temperature differences, having its own energy sources, etc., the ability to handle data, they need to make part of this bit of hardware, which not only is able to do the clever science, but then as an instrument capability. And so from our point of view, as an SME interested in taking this technology to market, we sort of targeted some industries. And in particular, we looked at aquaculture, because we regard aquaculture as one of the well, possibly the only way of sustainably produce fish protein in the coming years. And therefore, monitoring the quality of the water in these environments makes a lot of sense. Specifically, or especially, because recirculation fish farms, for instance, seem to be one of the ways forward. Not only because of the ability it gives you of controlling the parameters, and so your fish basically grows faster, but you protect it from the environment, so you, in theory, a lot more able to control pests and infections, etc. But then that poses specific challenges, and I thought it would be useful for us to run through a little bit of what was our attempt at seeing how do we make a sensor which we know can work in the laboratory, and then the different components work and provide a perfectly sensible response, but work in a typical fish farm. And when you go into a fish farm, you're talking about huge tanks, talking hundreds of cubic meters an hour, with high fish densities, high humidity, high temperature variations, staff that is used to deal with big, heavy equipment that you use crates and cranes to transport. You're not talking about delicate environment. You're not talking about delicate instruments that you use in the laboratory. So whatever you're going to design that has a commercial value and is useful needs to be suitable for those environments. And so that needs to be fed into the whole development process, and once you identify the challenges, or the fundamental scientific challenges, is how do you encase them into a piece of hardware which can handle these conditions. And this is one of the very strong potentials we see for this kind of technology. In the wastewater treatment, we've actually come across recently another very interesting application, which we were completely unaware of. But biomass plants, rather cleverly, are using sources of waste to produce energy. And in particular, when we're talking about, they're using old kitchen material as a source of timber for a gasification plant. But what that means is just whilst you're very cleverly using a resource which was going to be committed to landfill, you're also about to release all the products that were used to fabricate those wood composites, that some of them are 30, 50, 60 years old and are actually now banned products, but were well in use. So you will have to get rid of that and to prevent its discharge into the environment. Well, there will be techniques needed to monitor those streams, and not only that, you'll need technology to then remove them from the effluent streams generated. So our interest is in the removal of those compounds, but we need to access technology that tells us what they are, how much they are, and are they still there once we've gone through the treatment process. So the opportunities, the commercial opportunities are there, and I think they can only go one way, which is increasing, because the pressure we put on our resources is only going to be higher. The requirement for quality control is only going to be higher, and therefore we will have to develop the technology that meets those demands. Another quick example of applications is in the environment. I mean, and most of you will know this better than me, but again, deployment of instruments into lakes and something which you want to be able to leave there, collect the data, send you the data wirelessly. This kind of environment requires particular strategies in order to allow the instrument to cope with. We're talking about something which is autonomous. We're talking certainly about something which is wireless in its state of transmission. But again, the commercial requirements, the commercial demands are there. We're obviously more and more aware of the need for monitoring the quality of our water resources, and we'll have to do it in real time. And in order for that to happen, we'll have to have the instrumentation that allows us to do that. So the opportunities are there, and are for us to come up with the right hardware to meet those challenges. And I thought it would be useful to give a bit of a perspective, and I guess the market value is absolutely astronomical. And the requirements for technology are going to be different depending on the environments and the applications. But the point being that if the scientific know-how exists, and we know that we can do things in the laboratory, having engineering expertise to then take these pieces of know-how into the market is something which is a very sensible strategy in these kind of development projects, because if SMEs are going to exploit it, then or if SMEs are going to take the opportunity to exploit the market, then the opportunities are there. And it's just a matter of then having the right route to development to be able to develop this to market. And from that sense, radar has come up with a very relevant and sensible platform, or strategy, I should say. Rather than developing a specific sensor that will only be applicable to a contaminant or a range of contaminants, what radar is trying to do is putting a platform together. Something which then, with minimal modification, will cover a whole host of contaminants. And then as these come into the forefront of the environmental standards, it's a matter of developing the relevant assays that can target those compounds. And so what we think radar will provide then is a platform to not only carry out environmental monitoring over a wide range of applications, but it will also allow for further development to take place, because once the platform is well established, it's a matter of focusing on assay development for different applications. And I'm sure that all the partners in radar are happy to talk to anyone who wishes to discuss what are other future requirements. So I know that the scope of my presentation is quite different than the fundamental technical content of previous presentations. But I think the key message for us is this is an area of very important commercial value, and one well worth exploring, and all it requires is solid strategies of taking scientific knowledge to market and make use of engineering capabilities to be able to take that fundamental science into a product which is on the shelf and can be commercialized. Thank you.
Two things. First of all, I think I owe you some apologies because I called you Dr. Duarte, but I think I was confused. The name is Tito, but my uncle was named, the first name is Tito in Italian, so okay.
It's okay,
so,
it happens.
Okay, but since your name is not written in the program, so maybe it's Dr. Tito Duarte. or Dr. Duarte and Tito. Okay, now I think I interpret a little bit maybe the curiosity of the audience by asking you, could you just tell us a few words about what kind of electrochemical methods are used for the detoxification and remediation of water? Because we remain with the curiosity of knowing a little bit about it.
So Elysium's background technology is a coagulation technology, electrocoagulation. And so your industry standard in coagulation is addition of a precipitating agent, and normally iron and aluminium are the ones broadly used throughout industry. The only difference when you do it electrochemically is that instead of adding that through the dissolution of a metallic salt, so your ferric chloride, your aluminium sulfate, we do it through controlled corrosion. So what we have is electrochemical reactors, which are then fitted with metal plates, electrodes of specific materials. So different grades of steel, different grades of aluminium. You apply controlled currents, and what that does is allows you to dose very precisely and in real time those elements into solution. The big advantage of that is that the footprint for dosing iron or aluminium into a waste stream from an electrochemical reactor is orders of magnitude smaller than if you're doing it chemically. Because chemically you do it through solution, so your solutions can only be so much concentrated, and anyway they only have a concentration of iron and aluminium. So if you're talking about dosing a ton of iron, well, you need a ton of steel, or you need 1,001 kilograms of steel. If you do that through, say, a ferric chloride solution, you're talking about 20, 25 tons of solution that you need to store and handle, and it's highly corrosive. So electrocoagulation is one of the techniques. The other one are oxidation techniques, which you can or cannot combine with the coagulation. And then we also look quite a lot into advanced oxidation techniques, so using UV-assisted techniques to break down organic compounds. And in fact, that's one of the applications we're looking a lot into on the follow-up from radar, and developing techniques that are quite good at removing the trace levels of compounds such as endocrine disrupting compounds.
Okay, thank you. Are there more questions?